So how do we justify the performance of the hash table being constant time? Well, the performance of the hash table is based not on the size of a table, right? The size, how many items are in the table, but rather the proportion of items that are in the table over the amount of, the amount of items the table can hold. It's based off the load factor, right? With lists, the operations take more as you add more items, but for a hash table, the operation takes more as the capacity of the table is filled up. And this is kind of a subtle distinction, but it makes a huge difference. Think of a parking deck, right? Suppose you're trying to park in a parking deck. If it's 90% way full, right? 90% of the parking spots are filled, then it will take forever to find that parking spot. You will probably have to go up to the top of the parking deck and just, look for one of those few spots that are available. On the other hand, if, the parking deck is only half filled, then every other space is open, right? It takes no time at all to basically find a new space and just plop yourself down in it. And that's how that's the same kind of reasoning you can use to examine the performance of hash tables. The more sparsely populated your table is, the easier it is for a collision to get resolved, right? Because if there's no collision, well, we just transform the key into an index, insert it into the index, set it at that index in constant time, boom, you're done, right? It takes no time at all. But how long does it take for, that's assuming basically you've got your, you get lucky, you spotted something right away. So can we actually accurately define how long it's going to take you to find a spot to park your car, so to speak? And the answer is yes. So we've got this formula from Knuth of the Art of Computer Programming fame. So he's got this formula which says the expected number of comparisons, so not collisions, but this is the number of probes. So this includes you looking at the very first spot you're checking to make sure that it's empty or is it filled, right? So the expected number of comparisons you have to do is equal to 1/2 times 1 plus 1 minus L, right? Plus 1 over 1 minus L. And that L over there is the load factor, the percentage that the hash table is filled up. Now again, this is for open addressing with linear probing. So this means, right, the strategy is, if I can't put it in this spot, I'm going to look, right, if we have a collision in this spot, I'm going to look for the next available spot. And linear probing means the next available spot is literally the next one over, and if not that one, the next one over that, and so on and so forth, right? Adjacent. So let's take that formula for a spin, right? So let's go ahead and see how that works. So 1/2 plus 1/2 times 1 plus 1 minus L. So let's suppose that we are in a parking deck, right, or a hash table rather, that is 50% of the way full, right? So here, the load factor is 50%. 1 minus 0.5 gives us 0.5, which is 1/2. So I'll just go ahead and put 1/2 here. Now, in this case, we got to flip this over. All right, so this resolves into 2. So 1 plus 2 is, so this is equal to 3, and this will make that 1.5. So if we have to, so if we're looking to insert an item and the hash table is 50% of the way full, then it takes us between 1 to 2 checks, right? Checking, we can expect you can expect if it's 50% of the way full that you would look at the first spot and it might be open, or the next spot over, that's most likely going to be open too, right? It's a random process, so all the best we can say is that what the expected comparison is. What about if it's 75% of the way full, right? Kind of like the maximum for the hash table we built. 1, 0.5. So 1 minus 0.5 here becomes 0.25, right? So in that case, 1 over 0.25, that becomes 1 over 1 over 4. This is 4. 1 plus 4 is equal to 5, so that resolves fully into 2.5, right? So it takes a bit longer if it's 75% of the way filled. It's between 2 and 3 comparisons, right? And the reason for this is and so this is why I said earlier that if we need more, to get this time that we really want, this constant time, what we're doing is that we're sacrificing a whole lot of space, right? To make sure that these resolve, that these comparisons resolve quickly, these insertion operations, these deletion operations, they all will resolve quickly because we're capping what the maximum load factor is going to be, right? We cap it at 75% so that there's always going to be that easy open space to find. So if we continue that out, I'm going to skip to the next slide over here. Ignore the right hand over here because it's terrible, but we'll continue over here, right? If it's not filled, then boom, one comparison, find that spot. On the other hand, if it's halfway filled, right, again, between 1 to 2 comparisons over here, expected number of probes is 1.5, expected number of probes is 2.5, it's 75% of the way full. Even if it's 95% of the way full, only 10.5 comparisons, right? So now with chaining, remember you've got a linked list there. The L over here is not the load factor, but the average number of items in the list, right? It's the number of, well, it comes out to the same thing, but it's easier to think of L as the average number of items in the list. The number of items, so say we have 15 items, divide by the table size, and say our table, we've got 5 slots for, we've got 5 buckets. So 15 items divided by 5 buckets means 3 items per bucket on average, right? So chaining, so our equation is fairly straightforward there. It takes 1 to get to our chain and then to see if it's empty or not. And then if it isn't, we got to iterate through half the items in it to see if, on average, to see if the item is there. And so that's how many collisions we'd have. So that's not collisions, but that's how many comparisons we would need on average to solve that. So typically this L for this column over here might be something along the lines of 3 or 5. But 3 or 5 doesn't work for linear probing, so that's why it's not on the table. So how does this, so I'll continue in the next slide.